Hey kids, it's me, and today we are going to talk about molecular polarity. So first we'll talk about what a polar molecule is, and then we'll talk about how to determine the polarity of a molecule. So before we talk about what a polar molecule is, I want you to remember or recall what a polar bond is. So for example, a carbon-oxygen bond is a polar bond. It's polar because the oxygen's electronegativity, which is 3.5, is pretty significantly greater than carbon's electronegativity. And so oxygen is going to hog the electrons that are being shared between the carbon and the oxygen. So what you end up with is an unequal distribution of electrons. So this is your carbon and this is your oxygen. You'll notice that because there's more electrons around the oxygen, or those electrons are more around the oxygen, you get more electron density around the oxygen and less electron density around the carbon. So you end up with poles. One of them being a slightly negative pole because of those electrons, which are negatively charged, and the other one being a slightly positive pole on this molecule. All right, so let's apply the same logic to an entire molecule as opposed to just a bond between two atoms. So in this molecule, we actually have two bonds and we have these lone pairs on our central atom. And the way that this molecule is shaped is it's bent in a little V, like this. And the way that the bonds are is that the X in our compound has a higher electronegativity than the Y's, which makes both of these bonds polar. And that means that all the electrons are being pulled towards the X or up to the top of this molecule. So when you look at this molecule, we know this molecule is polar because the electrons are not evenly distributed throughout this entire molecule. There are clearly more electrons up at the top than there are at the bottom. So we get a pull of electrons from the bottom, or the Y parts of this molecule, up to the top. So what we are looking at is this molecule here has an uneven or an asymmetrical electron distribution. All the electrons, or most of the electrons, not all of them, there's a higher concentration of electrons on sort of this half of the molecule than there is on this half. So a nonpolar molecule would be a molecule with a roughly symmetrical or even electron distribution. So if we look at this molecule, you'll see that the electrons are all being pulled roughly towards the center, which means that this is a pretty symmetrical molecule. If I were to slice it, say, this direction, there's symmetrical on both sides. Or if I were to slice it in this direction, it's symmetrical on both sides. So there's a really even distribution of electrons in this molecule. So we would say it's nonpolar. So let's talk about how you would determine whether or not a molecule is polar. So to determine the polarity of a bond, you looked at electronegativity differences. It's a little more complicated when you're talking about an entire molecule that contains a bunch of different bonds. So I'm going to give you some steps, and these steps, if you follow them and you understand what you're doing, you should be able to determine the polarity of any molecule that I give you in class. So the first thing you're going to want to do is you're going to want to draw the Lewis dot diagram. There's no way around it. You have to draw the Lewis dot diagram if you want to determine whether or not a molecule is polar. So drawing the Lewis dot diagram for carbon dioxide, you would end up with a molecule or a Lewis dot diagram that looks something like this. So the second thing you would want to do is determine whether or not the bonds are polar. So in this case, our bonds are polar with the electrons being pulled away from the carbon and towards each oxygen. So these electrons are being pulled towards this oxygen, and these electrons are being pulled towards this oxygen. You should, at this point, feel pretty comfortable determining the polarity of a bond using electronegativity differences. Now, at this point, one of two things is going to happen. The first thing that could happen is that you would find that none of the bonds in that molecule are polar, in which case the entire molecule would not be polar. It would be a nonpolar molecule if none of the bonds are polar. Now, if just one of the bonds is polar, this doesn't apply, right? So you have to move on. But if none of the bonds is polar, then you can just say that the molecule is nonpolar and you're done. If you find that any of the bonds are polar, then you need to move on to the next step. So you're not going to assume the molecule's polar if the bonds are polar. That's not the same as this, right? You have to move on to the next step because a molecule can have polar bonds and still be a nonpolar molecule. All right, so this next step, again, if any of the bonds are polar, you're going to want to determine the molecular geometry using VSEPR. So that's the last video. You should have a table that will help you do this. So let's do this for carbon dioxide. So we notice that carbon dioxide has 2 electron domains. Both of them are bonded domains, no lone pairs. So 2 electron domains always means that you have a linear molecule. So that's its shape is linear. And you would then want to draw it as a linear molecule. Which it's already drawn as, but I'm just going to go ahead and redraw, as a straight line, as a linear molecule. All right, and the next thing you're going to do is determine the symmetry of electron distribution. And the way you're going to do that is you're going to use polarity arrows. So you remember that the polarity arrows look something like this. I suggest you use polarity arrows and not the partial positive, partial negative symbols because the arrows are more visual. So we already did that up here, right? We already determined that the bonds were polar. So we're just going to go ahead and draw those arrows back over the top of the drawing that shows the shape of the molecule. And what you're looking for is symmetry. So is this symmetrical? It is. These 2 arrows cancel each other out. One's going in one direction and the other is going in the other direction. And what you're going to find is that the electron distribution looks something like this. So you've got electrons distributed on the ends of this linear molecule, which means that the ends are both partially negative. So it doesn't have opposite poles. It doesn't have, and by the way, opposite poles are called dipoles. So it has no dipoles. It only has one kind of pole, a negative pole. It has a negative end and a negative end, no positive end. So this would be considered, and of course this is symmetrical, right? If you look at it, if you cut it this direction, it's symmetrical. If you cut it this direction, it's symmetrical. So it's symmetrical all the way around. This has symmetry. So it would be considered nonpolar. Okay, so let's do another example. In this case, or in this example, we are going to look at determine the polarity of carbon tetrahydride. So step number 1 says to draw the Lewis dot diagram. So the Lewis dot diagram for carbon tetrahydride would look something like this. So carbon bonded singly to 4 hydrogens. Step number 2 says to determine if the bonds are polar or not. So carbon has an electronegativity of 2.5 and hydrogen has an electronegativity of 2.1. So the difference between carbon and hydrogen is not enough. It's only 0.4 for each of these bonds to be considered not a polar bond. So every single one of these bonds is nonpolar. And what we said over here is that if none of the bonds is polar, then that makes the molecule a nonpolar molecule. So this is a nonpolar molecule because none of the bonds is polar. So we don't have to move on and do any of the rest of the steps because we've determined that the molecule is polar. And so really what that means is that the electrons are distributed around this molecule pretty evenly, so that if you were to cut it, say, this way or this way or this way or this way, it's symmetrical, or the electrons are distributed symmetrically all the way around. Okay, let's do another example. Let's do NH3. So NH3's Lewis dot diagram, step number 1, looks like this. Step number 2 is to determine the polarity of the bonds, and you will find that the molecule has polar bonds. So all of these bonds are polar up towards the nitrogen, which means that we don't get to stop here, that if any of the bonds are polar, we've got to move on. So let's draw a sketch of what this molecule would look like as far as its shape is concerned. So remember, using VSEPR, nitrogen, our central atom, has 1, 2, 3, 4 electron domains. 3 of them are bonded, and 1 of them is a lone pair. So that makes this a trigonal pyramidal shape. So a trigonal pyramidal looks like this. So we've got our nitrogen in the middle, and our hydrogens form the base of this pyramid. And then, of course, we have that lone pair up at the top. So step number 4 says that we need to determine the symmetry of electron distribution. So I'm going to draw those polarity arrows back on here. And you will notice that all of them point in the same direction. They all point towards the nitrogen, right? So they're all pointing up towards the nitrogen in the same direction. That implies that all the molecule, or all the electrons, are distributed unevenly towards the nitrogen. So if you were to look at the electron distribution, you would find that most of the electrons are congregating around the nitrogen and not so much around the hydrogens. So you would end up with this kind of weird asymmetrical distribution of electrons, all kind of in this direction. So what that tells me is that the nitrogen has a slightly negative charge, and then the bottom of this molecule has a slightly positive charge. So it's got dipoles. It's got a negative dipole and a positive dipole, which makes it a polar molecule. So that brings us to the end of our discussion of molecular polarity.